Well, the expression innate learning might be considered an oxymoron. It depends, I argue, that it's only an oxymoron if you have bought into the widespread assumption that the only theory of learning that counts is associationism in some kind or another, wherein it is argued there are no abstract concepts to start. Babies only are born with the capacity to form associations between stimuli and responses, and only to computate data that is at the sensory level. And by laws of frequency and contiguity, these little pieces getting together, and a little bigger and a little bigger, and then they get added to something else over here, and then these get put together, and eventually you get a percept, and then you have to go through the same thing again. Most importantly, it's a theory of passive learning, that if it's there, you will get it out of the environment by these laws of association. But I want to argue there are other possible theories of learning. And my view is, and I'm sure you'll recognize the influence of Jerry, that there are different kinds of structure mapping for different kinds of data. So for Fodor's position would be that there are encapsulated modules, and for me the idea is that there are core and non-core domains. Each of the domains has a different set of principles that provides the organized meaning of the content within that domain. And the domain as a mental structure, even in a skeletal form, is actively engaged in reacting to or even seeking out data that will add flesh to its structure. The data, however, have to share the same structure. And so you have the well-known cognitive psychology phenomena. If you have an organized database that has principles organizing them, you will willy-nilly interpret something that fits that structure. Sometimes you're right, but sometimes you're wrong. Fodor has an enormous influence on what I have to say today, and I'm sure you'll permit me to read you some from him. The paper entitled Some Reflections on Vygotsky, actually, if read carefully, is a devastating critique of stage theory of development. Stage theory of development has it that babies are born only responding to sensory data and perceptual data. Eventually they get to the point where they have something like true concepts, but not scientific reasoning ability until they're teenagers or older. Each of these are different mental formats. And one of the things Jerry pointed out is that for this theory to go forward, is that you're basically assuming some kind of feature theory and how you attach them to novel words. Further, both Vygotsky and Piaget make the mistake of assuming that logical hierarchies serve as structures for real concepts. And as he goes on to say, it's not clear that even adults organize their concepts in terms of formal logic. A third point in the paper is that Vygotsky's apparent adoption of prototype for structure of concepts won't do. And I'll have to remind this audience is you have a serious composition problem. I remind you of the pet fish not being made up of a typical fish in a typical pet. All right, if concepts, as Vygotsky proposes, we're continuing with Jerry, involve learning which perceptual features go with which words, then how do children and adults manage to understand one another? Especially the assumption that the word meanings are different. The answer we get back is they share the extension, but not the intention. Now, that leads to the next question, well, how do you know, if you don't have an intention, whether another extension belongs to the concept? And so it's a big oops. And Fodor goes on to point out, well, you know, there is this category of imaginaries, like imaginary playmates, fairies, witches, and so on, that all belong to the same intentional concept, and that young children use. They play at being fairies, wishes, they have imaginary playmates, and so on. Okay, so that's all we get by way of background, direct quotes in some cases from Fodor. And now, if I might, I'd like to turn to the notion of learning in a core domain. Actually, in domains, and the argument I start with is structure mapping is a fundamental learning mechanism. It's an active learning mechanism, as I said to start. If you have a concept of A, and somebody presents you another example of it, it fits. You might even go and look to see if your interpretation or prediction is consistent with that concept. And it does a lot of work. You might think of the notion of core domain as a bit like Chomsky's notion of learning organisms. Maybe. Because for me, the metaphor skeletal captures the essence of a core domain. That is, there will be learning about data that is directly relevant to the domain. It will attend to those stimuli in the environment that fit the structure. And the structure slowly starts to assimilate more and more data in a coherent way. They actively direct attention and permit the uptake of relevant data. And a very important point about young learners is there's a lot of self-directed learning. There's a lot of, oops, I made a mistake, or 1, 2, 6, 7, no, try that again. Or rehearsals at night that we've taught, the literature is full of. So if young children have some skeletal mental structures, they have a leg up when it comes to learning the data that fleshes in the relevant, by putting in relevant data. And of course then more learning can occur. So there is knowledge acquisition, there is learning. It's not as if I'm arguing that because there's innate skeletal structures, that knowledge springs forth as if from the head of Zeus, which seems to be the assumption amongst many developmentalists when you talk innate anything. Linguists do not expect us to think that babies will open their mouths and say, when are you going to change me? The first day they say a word. We know they worry about what is the learning theory that goes with innate inclinations to learn language in a syntactically orderly way. Let me also add, there has to be a variability. There is no assumption here of it's perfect. And in fact, there's an obligation to ask, is the variability noise or due to consistent alternative variables as, for example, conversational rules, as mentioned by our first speaker. By contrast, learning in non-core domains does not happen on the fly, save for a few precious geniuses like Mozart. The mastery of non-core domains takes time and effort. The learner has no skeletal structure to work with, as in the case of physics, chemistry, computer programming, philosophy, giving talks, and so on. You have to learn both what the data are and at the same time mount the data in a way that you can go towards a structure. So somehow you have to open a memory drawer for different kinds of chapters and stick it in there and hope the day will come that you'll say, oh, it's too messy, we've got to reorganize. And then you might get the principles organizing things. Okay, so I want to argue that the case of the number or the organization of the chart of numbers gives us a nice example of core versus non-core. By looking at rational numbers and integers. Integers are in purple or blue because they represent a core domain, and rational numbers do not represent a core domain. Of course, integers and rationals have to eventually become part of the same system for facts that are true about number, which is any number divided by itself yields an integer, and therefore, formally, integers do not stand alone, but psychologically they seem to do so. Because there's a unique mapping to the nonverbal underlying representation, numericity 1 must map multiplicatively 1 to the 1 identity. But when it comes to any continuous quantity and conventional mapping, the conventional mapping is only unique up to an arbitrary scale. There's an important change in our work, G&G being Randy and myself. It's that Randy has an analysis that treats the nonverbal representation of N as both discrete and approximate and not analog. And the reason this is important is we have to have unique successive value to represent unique N's. Structure mapping, which I will show you, is a computational account of the move from the nonverbal discrete to the verbal discrete. So here we have is an outline of the structure. Addition and subtraction at the bottom are principles, along with order and equals. These are formal concepts. And one way to get a cardinal value is to count. And if you're going to do that, when you have a set of objects, 1, 2, 3, 4, 5, or in a nonverbal representation, you must have one and only one tag representing each object that's in the structure, being in the collection. Whatever your order, the tags are, they must be in a repeatable order, because if they weren't, the result, which is the cardinal value, would not conserve over counts. And you need the cardinal value to do arithmetic on natural numbers. You can count any way you want. I can go 1, 2, 3, 4, 1, 2, 3, 4, as long as I count everything. And it doesn't matter what kind of objects you're counting. I can count all the minds in the room as long as I'm consistent. And that when I repeat that, I get the same answer Or if I don't get the same answer, I say, uh-oh, I made a calculation error. Okay? But you can't do addition and subtraction on the output of the count unless you've used these principles to guarantee you keep getting the same n. Or you conserve number. Somewhere, I don't, okay. All right, so now I'm going to turn to evidence in favor of a core natural counting, natural number system. And I'm going to start with infants and show you data that come from typically two methods. One's habituation, and the second's intermodal. This is the typical habituation paradigm. The baby is sitting up, maybe not, but when the baby is featured, looking at a screen or listening to something, and the same stimulus is played again and again and again. So, for example, you might play ba, ba, and they hear ba, ba, and they turn and look at it, or turn their head towards the speaker. But eventually, it gets a little boring, and they stop looking, or their head comes back. That's called habituation. And now you want to go in and ask, well, what happens if you change the stimulus, as opposed to continuing to play more? And if you change it from, let's say, 3 to 2 versus 3 to 3, will you get a preference for the novel input? Clear? And so let me just go back one. This is the standard habituation paradigm. The baby is watching or looking, and you're only testing one dimension, like sound, or whether the face is the same as the one you've been seeing, etc. Another method is intermodal, and now you're asking, are you going to get a match or a mismatch or not garbage? And here's a study that we did some time ago where the baby gets to look at 2 different stimuli with 3 on one side and 2 on the other. And what we're asking, and this is a very badly drawn perspective, do they tend to match the number of drum beats, boom, 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 with pictures of household objects? And those change across 8 trials before they repeat randomly. And the answer is yes, they do. But a lot of people have been skeptical. So I'm happy to be able to share with you a list of some of the studies that have replicated the intermodal finding, both between vision and sound, and vision and touch. So seeing things and touching is matched by number. The numbers are small, and I have to ask you to trust me that huge numbers of controls have to be run, or a whole bunch of different experiments to peel off possible confounds. We also now have data of addition in infants. The Koyabasi is particularly elegant, where they show babies 1 plus 1, one object plus 1 tone, and then it's equal to 2. Or 1 object plus 2 tones, and that's equal to 3. And then you get habituation across either of these conditions, and the wrong answer is what they get as the next one. And believe it or not, babies recover their interest. But this is not the only study. Karen Wynn, some years ago, published a paper showing babies were responding to 3 minus 1 in an appropriate way in a habituation study. As we move up the years, there are a number of other people who have shown that kids in their preschool years, on the assumption they're in an environment that has numbers in it, are able to solve simple addition and problems, and addition and subtraction problems. And actually, yeah, okay, that's all right. And some of the stuff that's coming out lately that's absolutely mind-blowing to me is that pre-verbal infants pay attention preferentially to a count sequence that's correct as opposed to incorrect or in another language. That's work out of Australia. There's another kind of work being done, is that if you have babies watch displays of numerosity 2, 3, 4, they're more likely to respond correctly to the sequence of 1, 2, 3. So this is before they're verbal. They're already picking up on the fact there's a list out there. I don't want to claim they know what it is. You can have one-to-one mapping without yet fully understanding it, and therefore get the learning off the ground for the language of counting you're born into. By the way, French babies respond to French sequences of counting, but not English, and vice versa for English-speaking Australian babies. So they are attending to relevant data and remembering enough of it to be able to show it has an effect on another task. Liz Brennan and her colleagues have shown that pre-verbal infants respond to ordered data so that you get transitivity. And by the time kids are just beginning to talk, we have shown that if you start out with 1 versus 2 or 3 versus 4, you get habituation to the first display pair, and then kids transfer to the second display. They don't overlap. The only thing in common is that they're ordered. And the thing that's most amazing is that when they get the transfer condition, they start spouting number words. And those turned out to be really important data because I could look at whether they were ordered or not over trials, and they are. You end up with some kids with idiosyncratic but systematic count lists. Not all. So there's more on addition and subtraction in preschoolers. Here's another procedure. The kid's a baker and he's putting up his donuts to sell, and somebody comes along with 3 pennies. Predict how many donuts will be left. And now, what do we have to add? So we do both taking away and adding. And 4-year-olds can deal with ends up to 9, 3-year-olds with ends up to 6. So these are addition and subtraction. And actually, it looks like they're pairing the addition and subtraction, but not intentionally. It shocked us that the system seemed to be recognizing inverses, and that turned out to be correct in a thesis done by Oznatzor. Another line of data is that you can have children play a game where they have to teach a puppet whether they're correct in their counting or not. So is the puppet double counting? Does it emit? Do they start in an unusual place, but everything's okay? What if they switch sides? Is that okay? And this is kind of the procedure, just to show you. We've got these all here. And in this task, it's the puppet did a double count and still ended up with the cardinal value, and the kid says, no, you can't do that. And sometimes they can tell you why. We're not claiming that they're articulating all the reasons. Another kind of task involves asking, let me go back, kids to count, tell us whether the puppet counted okay. So for example here, they're asked to make the third object be the number 2. And to get this right, they have to go over, back, and skip around. That's one solution. Another actually is to switch positions. And some kids do the latter, and kids can do this once they're about 3.5 years old. And then finally, most importantly, another kind of development, this shows up in other developmental topics, that kids who are involved in spontaneous counting are on their way to doing a better job at learning arithmetic later. So there is a deep individual difference. We don't know how much, but it's important to recognize that. It may be, and I think it is, related to environments and whether the culture has embedded in it opportunities to pick up on the way numbers are used. That's not always true. You don't learn to use your eyes if you don't get any light. So if you don't get data, you're not going to get learning with other skeletal mental structures. Now, an important point I have to make is that the skeletal structure gets things off the ground and it gets going. But it doesn't guarantee that English speakers or French speakers will crack the rule for generating the next number. French is particularly awkward. If you know, 80 is what, 240s. And it takes a while in English to get the data that tells you that there's a generative rule on a base 10. And it turns out that it takes a long time to learn the notation and conception of the notation for generating ever so larger numbers. But here we have some evidence that kids understand that the numbers keep going. If you tell them there is a number, a puppet can count to 361, and they get the idea that there are bigger and bigger numbers, then you can run them in what we call an infinity protocol successfully at 5 years of age. By which I mean, hey, think of a big number. The number is, kid says, 100. I said, well, what if you add 1 to that? Will that be bigger? And we keep going. And then we give them a number and say, I went home and I thought about what's a really big number. And it's a Google. And the kid says, no, that's not the last number. A Google in 1. Alternative, some kids will say things like, subject number 2, can you add 1 to that? We're in the thousands. Well, I guess we could announce in the newspaper that there is a new number that's called 1,000. All right? And it sort of comes back to one of the points that Tom made, is that they understand you have to share the language. And here is the language of counting. And they don't know the term, but if there's going to be a term, you better tell other people to use it as well. These kids are impossible to deal with. We run these infinity tasks and we say, don't tell your friends. They go immediately and tell them. We have set up a Kuhnian thought experiment. They come back and say, I know what you're going to ask me. And so we had to keep doing it, and finally that's the effect. They love thinking about what's going to happen if you keep adding and counting. Let's contrast that with, now let me make the final point here. The final point is, this is part of the natural number system, which is every time you add, you get a next. But let's take a look at rational numbers. Quickly, by third grade, kids get the idea that 0 is something like an identity, that it doesn't change the number, and they stop calling it nothing. So that's part of what the learning is, and they don't have that much difficulty with negative numbers unless the teacher says, we don't do negative numbers, which happened to my son in the first grade when they were asked to make up problems. So that kind of, extension keeps developing within the natural number system. And therefore, the core structure begets further learning about the core domain, but it doesn't facilitate learning in non-core domains. Rational numbers are a clear case of a non-core domain. For one reason is it's a tripartite symbol, and it's not going to map to the underlying nonverbal structure that I showed you, where every successive item is different, is separate. It's not continuous. And it's one cardinal value divided by another. We've introduced this word divide. It is not surprising to me, although it was to our math department, that children all the way to the 8th grade, and we'll see further on, interpret fractions as if they're natural numbers. I'll let you study this. Each number is on a card. They're asked to put them on a number cloth. They're given experience putting sticks in place, sticks the same length but different colors. They're told they can move things around. They can put things at the same place, etc. These are two different versions. This one's doing 2s, and this is doing the denominator by counting and putting 1 on top. And as you can see, it's a systematic, invented solution to rank ordering of fractions. Everybody can see that, right? And typically it's the case, the 2 should fell down. Oh yeah, there should be a 1 over the 2. It's often the case that with 0 and 1 off by itself, themselves, something special about them. Okay. We know, a lot of people have worked on this, myself included, and that you can get kids to stop making all of these mistakes and even transfer between decimals and fraction formats. But I've looked carefully over and over again through the literature. To my surprise, nobody's looking to see whether there's transfer to percent, which is what you really want. And you certainly would expect that once kids are in college, they can deal with percent. Especially in this day and age. These are within the last 3 years. Every day, the newspapers have sales of another 10% off, 50% off, and then another 10% off. Every night on the news, in the newspapers, the stock market went up 10%. Oops, it dropped 20%. Or it only dropped 2%. How much are your stocks worth? The answer is most are going to say, I have no idea. We asked every single kid in introductory psychology questions of the form. You start out with the price X. It goes up 50% and down. That's the simple. When you start at $100, it goes up 50% and then down 50%. What's the final price? And we varied that question. So here's the example of one of our questions in the first study. Use the plane ticket. Kind of thing that happens. And here are the results. No, it is the case that even more than 20% are wrong on the easiest version. If you ask it in an algebraic format, that is X goes up 50% and then down 50%, or the numeral version where they aren't used to that, it's even worse. These are the number correct. These are undergraduates. Here is the effect of their math background. This is a little weird, I'm sorry. Let's put the numeral and the algebraic should be reversed. Because what you're seeing, if they've taken calculus, which is in the slash crossbars, in the middle, well, they do better always, right? And they do better on the easiest one and they rank order. So there is an effect of at least some calculus.
Or did they self-select from going into calculus?
And here is another way of looking at the data, which shows you the number of how they solve, how they represent the results. And finally, mainly they're going to a decimal, which is nice. And we also know that when we rerun the study, using paper and pencil, this was on computer, but using paper and pencil, we not only replicate it, but we're able to trace the kinds of errors they're making. They're almost all conceptual after the first step. So there's a tendency to get the first problem right. That is, it goes up or down X%. But then they completely fall apart unless they have 2 years of calculus. So what we're seeing here is those individuals who have worked hard enough at learning mathematics to even go into the second year, by now they're in math, are much better at dealing with these typical percent changes they encounter every day in their environment. And now, for those of you who teach and put a graph up or talk about logs or anything else, it can't be surprising after the fact that students don't really understand what you're talking about. And there's deep misinterpretation because they assimilate it somehow to the natural core counting cardinal addition and subtraction problem. Okay? However, or in addition to and, I want to show you the potency of the nonverbal counting rules. One does 20. Oh, that's one. Which is 1 for 1, which has the constraint, do not double count. We showed undergraduates many demonstrations like this. The trees are in the foreground, and those trees could be seen through the window. These are all drawn. The horses are in the foreground, and they're reflected in the mirror. And finally, a picture frame. There is a significant effect of the type of frame. The main thing is people do not double count what's in a mirror. And they don't know they're not doing it. So it's not as if they say, oh, wait a minute, I can't do that. And it doesn't matter whether they label them or whatever. It's just done on the fly. And artists, I'm sure you realize, know this, especially, well, through the centuries. There are all these paintings with reflections out on a window where you see a different person or a different object, as opposed to in a window or a mirror. And no, most people say, oh, I never realized it, unless you're a professional interpreter of what's going on in the painting. So here we have the continued learning about the count list. Oh, by the way, undergraduates have a terrible time telling you how many zeros there are in a trillion. It's something you have to keep telling them every day. Well, how many? All right. So it's not as if the learning stops in that domain. It keeps going. And it even penetrates our perceptions without verbal statement. On the other hand, it gets in the way of learning a new domain. And that's because the domain not only already has a structure, it has a lot of content that overlaps, often in false ways, false cognates. And so you have to be able to somehow set aside what's in the core domain and take on the non-core domain as a real task of hard learning and hopefully with good teaching. I believe, that does give you an account of why some domains are universal. They learn relatively early and learn, quote, on the fly, often with help from other people. A kid asks a question, they get an answer, you hope. There are different mental structures of this kind. A small number compared to non-core domains. And they are the ones, I submit, that all people better have, if their culture is going to develop them, for them to communicate with each other and understand that they are sharing the same information. I thank you.
Okay, so I guess now it's time for questions.
So I wanted to ask about the.
I'm sorry?
What I wanted to ask about is the type of content in the core domain. I really like the idea of a
I'm
skeletal.
not hearing you.
Should I just go about this?
Is it on?
Have you got your really speak into it?
I really like the idea of a skeletal system. What I wanted to ask about is the content of the skeletal system. So you make it sound like the integers are almost in there. There's a lot of numerical content. You know,
I'm sorry, I guess my ear, the battery must have gone out. I'm sorry.
I wanted to ask about the skeletal system.
Yeah,
Okay. I'm curious about what
what
kind
do you think of that?
I'm curious about what kind of numerical content is in the skeletal system.
What kinds?
Yes. So, for example, how close are we getting to the integers sort of right from the start? And one of the reasons why I'm curious about this is because
Is the basic question is how many core domains, or?
it's essentially how many numerical core domains. So for example, one of the big debates that's happening right now, that I take it you're engaging with, is whether there's just sort of one core numerical system, or
I'm not hearing you.
Why is there
I
just,
think my batteries must have gone out.
can you guys hear me?
is there one core, he's asking, is there one core numerical system?
What?
He seemed to be asking, is there one core numerical system, or perhaps several?
Okay.
There's a reason behind this. Maybe Lila, you
All right.
can translate. The reason I'm asking,
I see. Is this culture specific? Right?
no,
Not one, I thought North America.
I'm sorry. What I'm asking about is in young children, so babies, whether there's
I
one,
really need to hear this. What's the matter? I think my batteries are gone. Why don't you come up here?
Yeah.
Yeah, why don't we get people standing up, because I really want answers. I'm sorry. I told everything, they're not working. Yeah.
what I'm interested in is whether there's one or two sort of core systems. And one of the reasons I'm interested in this is because if you look at the baby data, in some of the sort of most robust baby data, kind of the numerical discriminations that the babies can make sort of are limited. So, for example, there's a point where it looks like in certain tasks they could do 8 versus 16,
Well,
but not
yeah.
8 versus 12.
But that's coming under child.
But I noticed, I really like the Kobayashi study that you mentioned. And that's one where the ratio is actually 2 versus 3
I saw fabulous study.
for small number. And so that makes me wonder whether there's 2 systems, one for
I
small
don't
number.
think so. Okay. But, all right, he's asked a really deep question, which is, and there's an argument in the literature that most of these studies use small numbers, and the kids fail on larger numbers. And the best thing I can say is current studies coming out are showing more continuity. So more like they recognize you can prime with larger numbers and it has an effect. It shouldn't. It should be the same as a small set. And they're just very clever things being done. And there's a big debate about whether there's 1 or 2, even adults. And this is such a big question. But our studies, the one that people don't cite, with Sarah Cordes as a senior author, shows it's all the way down. I insisted we include 1 and 2 and 3, which people usually leave them out. And there's a big anchor problem in all those studies. If you're on a screen and you tell them what the last number is, you're of course going to get a curve. And there's a new study that just came out that got rid of that, and it's flat. The division of mean by variance is flat. So what's going on here is that, yeah, there's a bias towards the first few numbers. By the way, I think there's a serial position effect as well. So in studies that some people are starting to suggest this, I see it in our data, that kids might get the first 3 or 4 right, then start making mistakes. And we keep going up to 7, and then all of a sudden they're okay on 7. And this is a horrendous serial position task. Adults hate it. They do better at the beginning than the end. Oh, it's a well-known phenomenon in the literature. And so you get better learning at the beginning and better learning at the end. And whew, it's a standard curve. And then we did a long time ago stuff with up to 19 and plot 2 things, one, the range and the variance. But I also asked, are the kids answering in order with idiosyncratic lists? And the answer is, I think it was 2/3 were. And so, given that you expect variance due to a whole lot of important psychological performance variables, you've got to look at them. And you know, most of the literature doesn't. They only ask, do they get the last number right? I don't deny the small versus larger number effect. I started using it that way years ago. But kids were answering arithmetically. And also on the bakery store. They have to predict and then check. And when they check, they never make a mistake. Almost never. 3-year-olds. And it's a task they love. And when you ask kids just to count, they get pretty bored. They're going to say, I have to go to the bathroom. You have to know the stall. So, yeah, I don't think they're 2 systems.
Rochel, you have one question. I don't think this is working, is it? Is this microphone on? Okay, so do you, I'm sure you know the recent work
I'm
by
coming.
Charles Yang.
I'm coming.
Come on the way.
I can hear everybody. Yeah.
Recent work from Charles Yang.
What?
Recent,
Yes, I know. Yeah.
okay, that relates passing
I
something.
think he's wrong. He says those kids can count up to 89, then they can do the generation.
No.
What?
I mean, the effect that he found that I think is interesting is that being able to pass something like your infinity test varies cross-linguistically depending upon
The language.
the number at which
Yeah,
the
okay,
count
that's
system-
exactly, yeah.
the count system becomes generative.
Let me
So
translate it, yeah, okay. This was one that reminded me of work by Charles Yang, very interesting work. Language matters in the following sense, that being able to say or behave as if they know there's a next number varies across languages, and it should. Because languages vary in terms of the transparency of their base rule. Chinese, for example, is very regular in the sense it goes 1, 2, 3, up to 10, and then it's 10 plus 1, 2, 3, 4, 9. 2 10s plus 1. It is that way for a long time. It actually gets irregular. And when it does, the kids make a mistake. They do what our kids do. They use another word or whatever. This is Kevin Miller's work that was done many years ago. And of course, French is a nightmare,
Yes.
right? You're being able to get to 100 isn't going to do you anything to understand that when you go from 80 to 90, that you get a different phonetic composition of 100 is the next 10 word. And then there are cultures like I had the good fortune to be able to interview a senior gentleman who had come from Ethiopia, one of the Philashals, and we were able to do the right experiment. And but for me, that means first asking, what's your word in your language, not will you count the dolls. And I got to the point, it was clear he had a base, the language had a base 10, and then I asked about 1,000,000, and the answer comes back in Hebrew. And I said, well, that's Hebrew, and he heard me say that. And he says to his daughter and my friend, whoever had 1,000,000 things to count where I came from? Right? So, by the way, there's also very rapid assimilation of a better list when the culture encounters it. That I quote my sister-in-law, who was an Africanist. There are almost no languages left that are 1-2 combinations, but there are all over New Guinea, those islands, and I can give you a reference to a wonderful paper I just came across. And
On that note, I'll make a, can you guys hear me? Yeah. So now is going to be lunchtime between, I guess it's about 12 right now. So be back here at 12:30. I don't feel like this is over my, be back here, sorry, 2:30, never mind. And we have here information about places to eat that are around, and I have them organized by places that are closer, farther away. So some groups will be walking over to the student center if you want to go in groups, that's fine too. But let me know if you have any questions.
We're right
Here's
here.
information.